In 12.4, we're going to look at similar figures, theorems for determining similarity for triangles, properties of proportion for similar triangles, mid-segments of triangles and quadrilaterals, and indirect measurements using similar triangles. Let's suppose that triangle ABC is similar to triangle EDF. Then we have the following properties. This is only true if and only if the measure of angle A is congruent to the measure of angle E. The measure of angle B is congruent to the measure of angle D. And the measure of angle C is congruent to the measure of angle F. Another property that is true is the proportion of the side segments. AB over ED is equal to BC over DF, and that is also equal to the proportion AC over EF. Two polygons with the same number of vertices are similar if there is a one-to-one correspondence between the vertices of one and the vertices of the other, such that the corresponding interior angles are congruent and the corresponding sides are proportional. Just like in our previous definition, a polygon is similar to one another if there is a correspondence between the angles and there is a proportion with their sides. For triangles, we have side-side similarity. If the corresponding sides of two triangles are proportional, then the triangles are similar. Side-angle side similarity for triangles states, given two triangles, if two sides are proportional and the included angle are congruent, then the triangles are similar. Angle-angle similarity for triangles is if two angles of one triangle are congruent respectively to two angles of a second triangle, then the triangles are similar. So we only need two angles to be the same because the third one for a triangle is automatically the same. Let's try an example. For each figure, find a pair of similar triangles. Here we're given that the line segment AE is parallel to the line segment BD. So we know by one of our properties that this angle must be congruent to this angle. So the measure of angle CBD is congruent to the measure of angle CAE. Because these two lines are parallel and cut by a transversal, these two angles must be congruent. The measure of angle C is congruent to the measure of angle C because that's the same angle. So, by angle, we have the two triangles are similar. Triangle ACE is similar to triangle BCD. Let's try another example and see if we can find similar triangles. We're given here that BD intersects AE in the point C. Also in the problem, I know that the measure of angle B must be congruent to the measure of angle D because it's given that they are right angles. Also notice that angle BCA is a vertical angle to ECD. So these two must be equal to one another. So the measure of angle BCA is congruent to the measure of angle ECD. So by angle, we have the triangle ABC must be congruent to triangle EDC. Let's try another example in which we're given that triangle ABC is similar to triangle EDC. And the goal is to solve for x. Since these triangles are similar, we know that they are proportional. So AB over ED is equal to BC over DC, and that is also equal to AC over EC. So we can use any one of these proportions to solve for x. Since we're solving for x, the segment CD, I'm going to use the proportion with CD in it. So let's use BC over DC. And since we know AB and DE, we're going to use the proportion with AB and ED in it. So according to the proportion, we have AB, which is 5, over ED, which is 8, is equal to BC, which is equal to BC. In this case, I don't know what BC is, but I do know that the entire segment BD is 12. And part of it is x. So in order to find BC, this will actually be equivalent to 12 minus x. Because the whole length is 12, and we want to subtract x to find out what the segment BC is equivalent to. So it must be 12 minus x. And DC is x. And now we can solve this for x. Let's do the cross product. So 5 times x is 5x. And then we'll do 8 times 12 minus x. We'll distribute the 8 throughout the right side. So 5x is equal to 96 minus 8x. Let's add the 8x to both sides. 5x plus 8x is 13x, and that's equal to 96. Let's divide both sides by 13, and x is equal to 96 over 13. We have another property of proportions. If a line parallel to one side of a triangle intersects the other side, then it divides the two sides into proportional segments. Here we can say that y over x is equal to w over z, and x over y equals z over w. And that condition only occurs if the line segment BC is parallel with the line segment DE. I also want you to note that if there is a proportionality of the segments in this fashion, that automatically implies also that these lines are parallel. If they're parallel, the proportion is true, and if the proportion is true, then these lines are parallel. The mid-segment, or segment connecting the midpoints of two sides of a triangle, is parallel to the third side of the triangle and half as long. So a mid-segment is essentially a line that crosses the triangle in which the point M bisects the segment AB and the point N bisects the other segment BC. Also note, if a line bisects one side of a triangle and is parallel to a second side, then it bisects the third side and therefore is a mid-segment. So if this line MN and AC is parallel, and it bisects just one of the sides, it must bisect the other sides as well. In this example, we have a quadrilateral ABCD. In this example, we have a quadrilateral ABCD. The point M, N, P, and Q are the midpoints of the sides. What kind of quadrilateral is MNPQ? MNPQ. So we want to know what kind of quadrilateral is the quadrilateral in blue. And we're given that the point N, P, Q, and M are midpoints of the sides. That implies that the segment NP is a midsegment of triangle BCD. This implies the segment NP must be a midsegment of triangle BCD. NP is a midsegment of triangle BCD. Also, MQ must be a midsegment of triangle ABD. MQ is a mid-segment of triangle ADB. Since they're mid-segments, the line segment MQ must be parallel to BD. MQ must be parallel to BD, and NP must be parallel to BD. Since MQ and NP are parallel to BD, then MQ must be parallel to NP. If you construct a diagonal from A to C, you can do a similar proof and also prove that MN is parallel to QP. Since MQ is parallel to NP and MN is parallel to QP, we have that this quadrilateral must be a parallelogram. A median of a triangle is a segment connecting a vertex of the triangle to the midpoint of the opposite side. A triangle has three medians. The three medians are congruent. The point of intersection G is the center of gravity or the centroid of the triangle. Notice we have three medians. The first median is PC, and that bisects the segment AB. The second median is AM, and that bisects the segment BC. The third median is BN, and that bisects the segment AC. They meet at a single point at the point G, and that is known as the centroid or the center of gravity. The centroid also divides the medians into a ratio of 1 to 2. What that means is this segment MG is half as long as the segment AG. And that is for all of the medians. So this segment GN is half as long as the segment BG. And PG is half as long as the segment GC. Let's suppose we have the sun here and the rays of light are parallel with one another. We can assume this angle is equivalent to this angle, and we know that tree is perpendicular to the ground as well as our meter stick. So by angle, these two triangles must be similar to one another. So we can set a proportion. I could set up a proportion. I can say x over 40, this side over this side, is proportional to 1 over 2.5, this side over this side. And we could do the cross product again. So that multiplies to the cross product. So 40 is equal to 2.5x. And we could divide both sides by 2.5. And this gives us the height of the tree is equivalent to 16 meters.